In this video, we'll be going through examples of free body diagrams. When we analyze the forces acting on an object, we can draw a free body diagram. So what is a free body diagram? Imagine a diagram of a single object that shows all the forces acting on it. The idea is to depict all the forces that exist for the given object on its center of mass. Let's start by having a look at example 1, books on a table. Assuming that the mass is uniformly distributed, we can find and draw the center of mass, which will be in the middle of the books. This is shown by the green dot. Let's start by considering the vertical forces. We have a force acting upwards, and we call this the normal contact force, which is exerted by the table onto the books. This is indicated by the orange arrow. And we also have a force going downwards. This is the weight force exerted by the books onto the table, indicated by the blue arrow. As we know, weight is mass multiplied by gravity. Since the book is stationary, N and W are equal, and so there is no resultant force. There are no horizontal forces acting on the book as depicted in the diagram. Let's have a look at another example, where we have a car moving at a constant velocity. Assuming that the car's mass is uniformly distributed, we can draw the center of mass. Consider the vertical forces. We have the normal contact force acting upwards, and the weight of the car which act downwards. The forces acting on this moving car is the same as the books that are stationary in example 1. This is because the car is moving at a constant velocity. This means that there is no resultant force according to Newton's second law of motion. Therefore, no arrows are drawn horizontally. In example 3, we have a car decelerating due to friction or drag. Consider the vertical forces acting on the car. We can draw the normal contact force and the weight just like the example above. Now consider the horizontal forces. This time there is a frictional force that is making the car decelerate, moving oppositely to the direction of travel. In this example, we have an aeroplane accelerating and traveling horizontally. Considering the vertical forces, we can begin by labeling the upthrust force U. We then have the weight acting downwards. Now consider the horizontal forces. Since the aeroplane is accelerating, there is a driving force exerted by the engine labeled F. We also have the drag caused by the air that the aeroplane is traveling through. In this next example, we have a boat floating on water. What forces do you think are acting on this boat? You can pause the video and have a go. This boat is floating, but it isn't accelerating horizontally. This is an indication that there are no horizontal forces acting on it. So, consider the vertical forces. We have upthrust exerted by the water and the weight exerted by the boat. Okay, now moving on. In the examples 6 and 7, we have a ball attached to a light and extensible string. Let's start with one inextensible string suspended from a fixed point. What forces do you think are acting on the ball? Consider the vertical forces. Firstly, let's draw the center of mass. We have the tension of the string acting upwards and the weight of the ball acting downwards. There are no horizontal forces acting on this ball. Now we have a ball that is attached to two fixed points, A and B. What forces do you think are acting on the ball now? You can pause the video and have a go. Okay, let's draw the center of mass. So we have the tension forces acting along the strings and the weight of the ball acting downwards. The tension forces are at an angle to the vertical and horizontal axes. So if you were to resolve the forces, as it is stationary, both horizontal and vertical forces should be balanced. In the next example, we will look at a stationary ball on a smooth slope. Know that a smooth surface exerts no frictional force. Here we have a smooth slope with a ball attached to a light and extensible string. Considering the forces acting on the ball, we have the tension forces acting along the inextensible string, indicated by the red arrow. We also have the normal contact force acting perpendicular to the slope. Remember that the normal contact forces act perpendicular to the surface that the object is on. Finally, we have the weight of the ball acting straight downwards. If we connect the forces head to tail, it forms a closed loop. This closed loop means that there is no resultant force, for example, a stationary object. This is also the case for objects moving at a constant velocity. Moving on to example 9, we want to find the forces at an instant when a tennis ball is dropped from a building at rest. So, we have a tennis ball at rest. We draw the center of mass and consider the vertical forces. We have the weight of the ball but no normal contact force. This is because the ball is not touching the building at the instant that it drops. In this final example, we are considering the same tennis ball that has reached its terminal velocity. Since the ball is dropping, we can draw out the drag force caused by the air which is acting upwards, and the weight of the ball acting downwards. If an object has reached a terminal velocity, it means that the maximum velocity attainable by an object as it falls through the air has been reached. So d equals w, resulting in zero resultant force. If we have a look at the graphical representation of this free fall, we can see that the velocity plateaus from point D to E. This is when the ball reaches its terminal velocity. Let's have a look at the free body diagram of the ball at these specific points. At point A, we know that the only force acting on the ball is the weight, as it is at rest. At point B, we start to see the opposing upthrust force. At point C, the upthrust force increases and keeps increasing until points D to E, where the ball reaches a terminal velocity, and the opposing forces are in equilibrium. The ball is accelerating between points A and C, meaning that the gradient of the graph is non-zero. Well, that's it for this video. If you have any questions or are unsure about anything, please leave a comment below. For those of you who are on social media, check out our Leornian TikTok page where we answer exam questions in quick and simple methods to help you revise or to use as cue cards. Thank you for watching. Please like and subscribe for more.